I'll continue with the half plane range counting. In the last class, we talked about half plane range reporting, and then we discussed if you allow quadratic space, how one can answer half plane range counting in logarithmic time. Today, I want to give you a somewhat different solution, which also extends to higher dimensions, and also the technique that I will use here will be useful for the other extreme when we have only linear space and we want to answer queries efficiently. So, half plane is called half space in high dimensions. The notion that I want to introduce today is called cuttings. So, I will describe it in 2D, and then you can think about in high dimensions as well the same concept. So, suppose you are given a set of lines. So, L is a triangulation of plane is a planar subdivision So, triangulation is a planar subdivision in the plane if I am talking about 2D triangulation. Now, there is one technicality that we are talking about the entire plane. So, some of the triangles will be unbounded because plane is infinite. So, we define the triangle as an intersection of 3 half planes. So, this way basically that is what I was trying to draw that, but that is our technicality, but you think about a triangulation. So, 1 over r cutting, so you have a triangulation a triangulation is called of 1 over r cutting of L if every triangle intersects at most n over r lines of L. So, it means that what you want to do is have a triangulation something like this, red lines. These vertices of the triangulation have nothing to do with the arrangement, they can lie anywhere. What you need is property that if you take any triangle and you count the number of lines that intersect the triangle, they are only at most n over r. So, every triangle intersects a few lines, not a Now, there is one technicality that I should point out, and that is the following. So, suppose you have a situation that all lines pass through a single point, am I right? Then if that is the case, then does not matter what triangulation you use, this point will lie in some triangle, and that triangle, if this point the n line passes through this point, then you say, well, you cannot have such a condition because this will there is no way that you can have a cutting 1 over r cutting because all n lines pass through a single point. So, if that is the case, we need to come up with a more technical definition. So, what happens is when you go back to triangulation, then what is called a complex simplicial complex. If you remember that a vertex is a 0 degree simplex and an edge is a one dimensional simplex, and a triangle is a two-dimensional simplex. Right. So, what you sort of say is that you define the cutting, that you have a triangulation such that if you take any simplex, and now when I talk about the triangle or any simplex, these are open, because when you think about this triangle, two-dimensional triangle, you do not count its boundary, you just take the interior. Similarly, when you talk about this edge, you look at only the interior of this edge, you do not count its endpoint. Endpoints are counted only at the vertices. So, you say, then you say sort of says that triangulation is a cutting if every interior, if every triangle or every simplex crosses n over at most n over r lines. So, every simplex crosses, what this it means is we say a line crosses a simplex if line intersects the simplex, but line does not contain the simplex, right. So, for example, if you have lot of these lines passing through a single vertex, you do not care about those lines, that is not do not count, because for vertex the crossing does not make sense. Now, in the case of edges, you look at the things that only passes through the interior, the crosses, you do not consider the line that contains this edge. So, that is a technicality which becomes even more important in high dimensions, but I will be sloppy and I will use the definition that I wrote on the slide. U, sorry. So, this I should write it, maybe I should use S, that is fine. So, the question is, what is the size of a 1 over r cutting? If you want to have this condition, if you want like to have this condition, then how many triangles do you need? And here is a theorem. Given L and R, a 1 over r cutting can you read it, or it is not good color? Okay. Let me try this one. Okay, so that is a theorem. What it says is that there is a cutting of size order of r square. So, one thing is that first thing you observe is the size of the cutting depends on r, but not on n, it is independent of n. So, it does not matter how many lines you have, there is always a cutting of size r square, and it can be constructed in time order of n r. Now, first I should tell you that this is the right answer, because you cannot hope to do better than r square. And here is a simple argument. Now, if you take n lines, you take n lines, how many vertices are there in the arrangement? And choose 2, am I right? There are n square, I will ignore the constant, there are n square vertices. If a triangle contains only n over r lines, how many vertices it can contain? Pardon? And well, be a little more precise, because I am not sure where the by shows up. When you say n by r choose 2, or so where does, did you mean n denominator r choose 2 denominator, or you n by r in the, so you mean, that is what you mean, right. So, this is not, So, this is saying it is n square over r square, right, because you have n over r lines. So, quadratic, it is what you should think about is we have whatever k lines, then you have a k square vertices. If you only n over r lines intersecting it, you will not have more than n square r square vertices there. So, if a triangle can contains only n square over r square vertices, and this is triangulation of the all plane, each vertex has to lie in one of the triangles. So, you need at least r square triangles to cover all the vertices. So, that says that r square is the best you can hope for. So, this is asymptotically the best one can do. Now, I will not give you the proof, and I will defer it to my esteemed colleague Sandeep. He will do it when he teaches next either Friday or next week. And it's a very fundamental result in geometry, and it is used to develop many geometric data structures, as you will see here, but also for many divide and conquer algorithms. It's okay. So, that's a theorem. Now, it's also true in high dimensions. In high dimensions, triangle becomes simplices, and you have hyperplanes. So, instead of lines, you have hyperplanes in d dimensions, and triangles become simplices. And then what is known is the following: the size becomes r to power d, and this becomes r d minus 1. So, you pay a factor of r for each dimension. That's what you should think about. Now, why is this result interesting in the context of half plane range counting? For that, I need one more concept, and that I will call cutting tree data structure. You think about. So, cutting tree is computing a cuttings recursively. Okay. So, choose a constant r 0, okay. And what you are going to do is you are going to compute the cuttings recursively. So, in the beginning you have all lines, let us say given a set of lines L. So, you have set of lines. What you do, you choose a constant r 0, you compute 1 over r 0 cutting. Okay. So, at the root you compute a 1 over r 0 cutting. So, it will have r 0s, I will ignore the constant, you have r 0 square triangles. For each triangle intersects roughly n over r 0 lines, and you do the cutting for those lines again. Okay. So, you get for each triangle, each child corresponds to one of the triangles of the cutting. So, I will write it more formally on the slide, but just first want to give you the idea. So, you compute a cutting, take a triangle of the cutting, look at the lines that intersect it, you compute the cutting again for those lines, and do it again. Now, you get another set of triangles. For each triangle, now you look at which lines it intersects, you do the cutting again, and you keep on doing it until you are left with very few lines. Now, let me write it formally. Let me, since I am defining a recursive procedure, let me sort of do the following. Recursively, let us say instead of H is the current set of lines, and delta is a triangle that these lines intersect. Initially, delta is the entire plane, because at the root. So, let us call this one as tau 1, tau s. So, you compute a cutting of these lines. uh, let hi be the set of lines intersecting tau I. Okay. Make each tau I a child of delta, and then you can say compute the cutting tree recursively on hi and tau I for all. Okay. So, what happens is that if you think about it, initially you have a set of lines, I compute a cutting, something like this. Now, I pick up a triangle in this cutting, look at the lines that intersect it, and I compute another cutting here. Something like this. Now, you have another triangle, recursively look at the, here there are only two lines, maybe you will stop it because R 0 is that is more than 2, otherwise you recursively compute, keep on doing it again, right. So, this is a so this way you get a tree, because when you look at the, if you unravel all the recursion, what you're getting a tree, and the fan out of the tree is large, it's R 0 square, because the size of cutting is R 0 square, or some constant times R 0 square. Okay. Does this make sense, or should I repeat this cutting tree?
When you are doing the translation using that, so the results you do are they important after you are doing the product translation?
Good question. You will see why they are important, because so what you think about is that you are getting a tree, am I right? Each node of the tree is associated with a triangle for which you constructed. Okay. Now, final stuff that you have is corresponds to the leaf. Okay. So, let us say suppose you build a tree. Okay. So, the leaves, the nodes, leaf nodes you have here, you have a triangles, they are the finest triangles. Okay. And then the nodes here, interior nodes, they will correspond to the bigger triangles that you have constructed. And you will see that these triangles will help us to guide a search, because otherwise if you land up here, then it will be a problem. You will see in a minute when I talk about that. Now, the question is why I talked about cutting tree. What I want to show you is that you can use the cutting trees to answer half plane range counting query, and this works in higher dimensions also. So, remember that what is a half plane range counting in the dual? You have a set of lines, and when I give you a query point, tell me how many lines lie above this point, right. That was the problem. Now, in 2D, we were lucky we could compute the arrangement, and we could compute this, we had that just ready-made data structure, point location data structure. But I don't know if Sandeep talked, now you can, there is a point location data structure in 3D as well. The running time is, query time is not log n, it is log square n, but in higher dimensions, it is not clear how you do point location in general in subdivision. So, this technique does not extend to higher dimensions, and the cutting tree you will see works in higher dimensions as well. So, now if I use, how do I use cutting tree? Using, how do you use cutting tree to solve this problem? Can someone think about it? Just to remind you that each node here has a triangle associated with it, and let us say a set of lines h delta, which are lines intersecting there. And then you computed a cutting, and then you got a refinement of this triangle. What I showed you here. So, if you look at this data structure, look at the stuff, how will you answer? You have to store some additional information at each node, but then how will you answer half plane range count? So if you look at a cutting, am I right? Not all lines will intersect a triangle. So if you think about it, so let's say, let me draw some more lines. Let's say some pattern. Now I focus on this triangle. 2 lines or 3 lines, they are intersecting this triangle. Okay. So if I know that, as what he said, suppose if I know that the query point lies here. Suppose it lies here. Now the lines that intersected this triangle, I have no clue whether they lie above or below. But the lines that do not lie intersect this triangle, I know, am I right? That for any point inside this triangle, the answer will be the same. So if a line lies below the triangle, that doesn't matter where the query point lies inside this triangle, this line will lie below this point. And if a line lies above the triangle, doesn't matter where the query point lies inside that triangle, I know that this line will lie above this point. So what I can do is, since I care about the lines lying above the point, for this triangle, what I do for each triangle, I store the number of lines that lie above this triangle. Okay. So what you do is you modify this construction. For each type, you store the number of lines of H. Alright, so I store this. Now I do it at every node. Okay. So now what I know is, once I know query point lies inside this red triangle, I know that these 2 lines lie above it. I have counted them. This I don't care. Now I have to worry about the lines that intersect this triangle. Now there is a second level cutting, green cutting, for these lines. Now again I know that lies inside here. Well, in this picture there is no other line. Suppose if you had also had this line, then now I know that if I know that the point lies this triangle, that this line lies above it. So I can add these quantities. Now I need to figure out only about these 2 points. So I go back to this, go down in this tree. No, because I already counted them. So you only worry about the lines that intersect the red triangle. Because the lines that do not intersect the red triangle, so I only need to worry about the next level. I only have to worry about the lines that intersect this triangle. So I count them. So the query procedure becomes the following. Let's call this quantity as n tau I. So query that's at a node W. If delta is a leaf, return the number of lines of H delta lying. Oh, there has to be a query point also. So if you think about the tree, what's happening recursively, you are at a node, some delta on this tree. You have if it is a leaf, then there's nothing there, so you just count, because there are only R0 lines. If you remember that the condition for a node is a leaf only if there are at most R0 lines there, and R0 is a constant. So just look at the constant number of lines, figure out which of them lie above it, count that quantity, and return it. Else, let tau be the triangle of cutting is stored there that contains P. Okay. Otherwise, you find the triangle. For example, in this case, you found the triangle in the red triangle that contained the query point. And then what you do is you return the value and tau. So, how many triangles lie above this red triangle, plus recursively count the things here, plus query. Okay, so that's the procedure. So, what it sort of says is that, let us say, look at this node. If it's a leaf, just count the number of lines explicitly that lie above it, because they are only constant for those lines. Otherwise, find the triangle that contains the query point. You have already stored how many lines lie above this triangle. You have that quantity. Take that quantity, and then recursively among the lines that intersect the triangle, you count the number of lines lie above the query point recursively and add that quantity to it. That's the procedure. Okay. So, what's the query time? So, what will be the query time? So you are following the path, right? Say it again. Okay, so that's a good question. I will answer your question a little later, because that will be more about the size of the data structure, right? Because so in terms of query, what's the query will be that will be what's the depth of the tree. Pardon? So remember R0 is a constant, log of n, right? Because it will log n to the base R0, because what happens, you start with n lines, and then you get n over R0, then the fraction, you decrease in size by fraction. So the depth of the tree is log n. Ignore the constant R0 for now, and you spend constant time at each node in this query procedure. So the query time is log n. Now let's answer his question: how many leaves are there? Because since it's a tree, the total size of the tree will be proportional to the number of leaves, right? So let's say Sn is the size of data. So we say, let's say, number of leaves in the cutting tree built on n lines. So maximum number of leaves in a cutting tree built on n lines. Okay. So what's the size? If oops. So if n is less than R0, then it's a leaf, so it's only one. So there's only one leaf. So interesting cases when n is bigger than R0. Then what happens? How many leaves? Then what happens? So what's the recursive formula you will have? So think about that Sn is, you are counting the number of leaves in this rooted subtree here, right? So what will the recursive formula you will write? Yes. So because the number of leaves is the number of leaves in each of these subtrees, right, rooted at each of the children, right? There are R0 square, the number of things here, number of children, and each of them has only at most n over R0 lines. Now you have to be a little careful, because this order of R0 square, and that will give us some headache, because it's not precisely R0 square, there's a constant. So what, let's write it, it is C times R0 square and S 0. That is the number of leaves. So, let us look at this recurrence, what happens to this recurrence. So, if you start expanding it, what will happen is, if you expand it I times, what will you get? You will get C times R 0 square power I times S, am I right? Because every time you size becomes, so if you want to go little slowly, so S n I wrote as C times R 0 square S. So, next time when you do it, am I right? Because you lose another R 0 factor. So, which is C R 0. So, when you do the third time, you will get right. So, that is what you get the recurrence. Now, when does the recurrence stop? When n becomes R 0. So, this is so when n over R 0 I becomes R 0, or if you want to sort of say maybe 1, it becomes like it becomes. So, let us say, so I becomes roughly log to base R 0 n. So, now if you look write it here, and then when it becomes you reach here, then you get S of R 0, it is basically 1, am I right? So, this size is C R 0 square log of R 0 n. Now, this looks little nasty, so let us handle it carefully. So, this is C log R 0 n times R 0 square so let us talk about this one. What is this term? This is n square, am I right? But you have this, this also you can write in a different form. So, this you can write, if I will not, if you do manipulations in log, this is saying it is n log R 0 C, am I right? So, the size of data set would have been n square except this nasty little this term. Now, R 0 is a constant that I choose, and C is a constant that is coming from the size of the cutting. So, I can choose R 0 as large as I want, large constant, and by making R 0 larger, I can reduce this term as small as I want to any sort of constant. But what I pay is, I did some cheating here in the log n, is actually the log n here is R 0 times square log n, right, because there is a tree here. At each node, you need to figure out which of the tree contains the query point. So, you have to spend R 0 square time here. So, you spend R 0. So, what happens is that you can make the if you make R 0 large, what is happening, you are increasing the fan out, tree is becoming shrinking, depth is shrinking, but fan out is increasing, you spend more time at each node. So, that sort of says you cannot make it arbitrarily small to. So, normally what you write it is basically I give you some parameter epsilon, say, and then you can say the running time is at most n to the power 2 plus epsilon, and given epsilon you can choose R 0 to be sufficiently large constant that will depend on epsilon. Okay. Any questions about this? Now, let me move to linear size data structure. Now, remember that the points are in convex position. When we talk about the range reporting, what I said was if the points were in convex position, then I knew that the query line intersects this polygon at only 2 points, am I right? So, you can think about that if you erase one edge of the polygon, and here is a set of points. You can think about the remaining polygonal chain. This is what is called a spanning path, like a spanning tree, right? Because a spanning tree is a tree that whose vertices are the precisely the vertices, the input the points of the graph. And this is a path, so it's a spanning path because it contains each vertex is one of the input points. It covers all the input points. So if the points are in convex position, we have a very nice property that if you take any line, it intersects the point the path at only 2 points. Now, if the points are not in convex position, then what happens? So suppose then you cannot be so lucky, right? That because if you look at a spanning path, it is going to intersect the line more than 2 points. So question you ask is the following: if you are given a set of points, construct a spanning path such that every line, let us call it pi, of S as few edges of pi as possible. Okay. So, what I want to do is I give you a set of points. Maybe let me now I want to construct a path with the points that every line should intersect this path at only should intersect few edges of the path. Now, before we say what we can do, let me tell you why we want this. Now, suppose if I have a line this is line M. Look at the intersection point. Suppose it intersects here in only these 2 edge points. Then what you know is that between these 2 intersection points, which was the same property here, that either all of the points lie above the line or all of them lie below the line. Am I right? So, if I tell you that this line intersects this spanning path at only a few places, and I can also find those intersection points quickly, then I can answer the query, because then what I need to know is that how many points lie below it. And since this path is a linear order, if I know the index of the vertices of the intersection points, I can subtract and I can tell you that how many points lie there, right. So, suppose you have a path and here is a line. Well, maybe this is too good to be true, but let us say it's then suppose I can find each intersection point quickly. Let us not worry about finding the intersection points. Then what I do is that let us say this is the I restore the index 1, 2, 3, 5, 6. Right. If I tell you that this is the edge, you know this index, then you know that how many points lie here. There you can find them. Similarly, well, rest will lie below, but suppose if the path went something like this up, again you can do this one. And the time you will spend, the number of things that you have to add will be proportional to the number of intersection points. So, if I can tell you that there are very few intersection points, then that's good, and if you can find them. Now, for the convex case, you were very lucky because there are only 2 intersection points, but you won't be so lucky for non-convex case. So, this motivates this problem, what is called finding a spanning path with a small crossing number, because the line. So, this is called a spanning path Okay. Yeah, question, go ahead. Well, I haven't told you yet. That's what I'm going to tell you next. And I haven't told you what the answer you should expect, that how many lines intersect. So you are just one step ahead of me if you. So let's ask the following. Let's just answer his question, what question he raised. That's what I was going to do it. So let's do introduce some notation. So so for a path pi and a line L, let's say the number of crossing points. Number of crossing points is the number of this edges it crosses. Okay, so this is for a fixed line, for a fixed path, you say look at it. Then I define the quantity, that's a crossing number for pi, is a maximum over all lines okay, and that's for a given path. You look at the what's the maximum, for what's the worst you can have. Now what you want to do is, for given a set of points, you want to construct a path that minimizes quantity. So the maximum number of lines you do it. So question you ask is, how large is chi of S will be? So question you want to ask is, what is the value is? So does anyone want to make a guess? Yeah, so I was going to come to that, like basically, so for what's a worst case bound. So if like Sandeep, what Sandeep said, then maybe I should introduce another thing. Is if you take a set of n points, what's the worst thing that happen? So the question is, what's the value of chi of n? What does your intuition say? So what about points on a grid? Suppose you take a grid points, you take a root n by root n grid. What do you think the answer will be for that? Pardon? Sorry, say it again. Why would it be order n? Because you are taking root n by root n grid. Root n root 7, right? Because if you let's say just take, let's say this, take this is a spanning path. Now if you take any line, it will intersect each column only once, each vertical line only once, am I right? So they will intersect only root n edges. So for grid you can do root n, and you can also convince, which this requires a little more work, convince that you cannot do better than root n for the grid. Because it doesn't matter, but this is one way of construct. It doesn't matter how you construct a spanning path for this grid points, you will stuck with root n. So root n is a lower bound for chi n. So this is we know that it's a root n is a lower bound. The question is, I know that for grid points I can do square root of n, but and when I say square root of n, I mean order of square root of n, and but can I do it for any point set? And it turns out this is it is indeed the case. This is you can do it. Okay, and what I will do is I will give you a very quick. So can I afford to go a little over time? So it might not be recorded, but you can hear. The tape might not be this. Okay. So let me first describe the construction, and then I'll do analysis. The reason I want to do this analysis is very cute, and it has similar ideas used in many different places too. So now, and the proof is a constructive. So I'll give you an algorithm how I construct the path. So remember that. So what we have is you have a set of n points. you have a set of points. I want to construct a path, so that every line intersects at most, again I will forget the constant and square root of n edges. What I will do is, I will, it is like a algorithm you have seen for computing minimum spanning tree. I will add one edge at a time. So, the algorithm will work in n minus 1 phases. In each phase, I will add one edge to it. So, what will happen is that I will be maintaining a collection of paths at any given time. Okay. So, in the ith phase, after I finish I phases, I would have added I edges, and you will have a collection of paths basically. So, you will have something like maybe something like this, maybe something like this you will have. Okay. So, let me describe you what I do and how I choose a new edge at each stuff, right, and that is a construct. So, now let me do the following. Now, other thing you observe is the following: although number of lines are infinite, but if you have a set of points, you only have to worry about the lines that pass through a pair of points, because suppose if you have two lines, so that the same set of points lie above it and same subset of points lie below it, then these two lines will intersect the same set of edges of the spanning path, right. So, I do not have to worry about, I can think of these two lines as the same. So, what I can do is, I can just choose lines which through pass a pair of points, and that can be sort of the set of representative lines with respect to which I need to construct the path. So, what you have is, you have a set of points and you have a set of representative lines, and in the worst case you choose n square lines, but actually what it turns out that you have to choose a very small set of lines, but I will not go into that. So, you have a set S, set of n points, and you have a set L, the set of m lines. Okay. Now, what I will do is, lines will become weighted. Okay. So, there will be a weight function. Initially, the weight of each line will be 1, but weights will increase, because what will happen is, when I find an edge, and if I find a line intersects this edge, then I will increase its weight, because say, hey, this line has already intersected some edges. So, be careful in the future that do not add the edges that this line intersects, penalize it. So, that is the intuition. Okay. So, in the ith step I do the following. So, you have some paths, so set Si is the following. For each of them, you pick one of the endpoints. In the beginning, you have Si will be the same as set S, because will be. So, Si is a endpoint, one endpoint from each connected component. What will the size of Si will be? Because after the I stuff, this is because you have added I minus 1 edges, am I right? Because in the after I steps, I have done the because you finished. I am talking about ith step. So, I finished I minus 1 step. So, I have added I minus 1 edges, right. So, the number of points that you will choosing will be n minus I plus 1, right, because in the first one you will have all the stuff, and then you added one edge, one point disappears, and so on. That will be the case. Okay. And let us call this as Ni, just to make my notation a little simpler. Now, I should say one more thing. When I introduce a cutting, this cutting was introduced for unweighted set of lines. Now, you have a weighted set of lines. So, here you think about this is a special case when the weight of each line is 1, and that is how the total weight was n, am I right. Now, if you have weighted lines, then you say that you do not care about n. What you want to say is that now if every triangle, so this statement will change to following. the weight of lines intersecting any triangle is at most total weight over R, because that is a generalization, because n was the total weight of lines when the weight of line the weight of each line is 1. If you look at the if you have weighted lines, look at the total weight, you want to say that none of the triangle is too heavy. The weight of the lines intersecting any triangle is at most total weight over R, and this theorem still holds. Okay. With those two things I am all set. What I do is choose a constant alpha, which I will tell you in a minute, and compute a so R is, this is a value, this is 1 over R, right. R basically is, so if you want to think about it, then R I have chosen is, this is the value of, so you think about this is 1 over R I cutting, I am computing. Okay. Now, the size of the cutting, so compute a cutting, let us call it chi I. So, size of chi I is order of R I square, is order of n I, sorry, which is n I square over alpha. If I choose alpha to be sufficiently large, this is, I can make this quantity to be n I minus 1. Right, because, or if one, so by choosing parameter, because you have a constant c, if I choose alpha to be bigger than the constant c in the cutting, then this will become less than n minus 1. Does this make sense, or I lost you? So, size of the 1 over I cutting is out of R I square, R I was root n I over alpha, so you get, sorry, n I over alpha square. So, you get by choosing, if you choose alpha to be sufficiently large, this quantity will be n I minus 1. Now, what I know is number of points is n I, number of triangles is at most n I minus 1 in the cutting. So, here is a cutting, suppose, and then you have some unbounded triangles. Okay. Now, the number of triangles is at most n I minus 1, is at most n I minus 1, and the number of points is n I. It means there is a one triangle that contains at least 2 points. So, it means that you have a situation that you have a triangle that contains 2 points by pigeonhole principle, because n I points are lying inside n I minus 1 triangles, then there has to be at least one triangle that contains at least 2 points. All right. So, you can add this edge to your spanning path. So, it means there exists a triangle that contains 2 points, let us call them P Q. So, add P Q, phi Q. So, that is a construction. Okay, not yet, one more step, and then for each line in L that intersects P Q, set double its weight. So, this is a point P Q, and suppose this was a line L that intersects this edge that you just added, you double its weight. because you want to penalize it, because now you know that this line intersects this edge. So, you want to be careful, because you do not want to choose another edge that intersects this line. Oh, you want to choose, but you want to decrease the probability of choosing that edge. That is intuition. Okay. Any questions about the algorithm? No, there is no query. This is just construction of the path. Pardon? So, these are set of lines you had, right? So, the construction I had, you started with a set of points and I had set of lines. I said that lines were all the take the what I have argued that it is enough to look at the lines that pass through pair of points, right? Because this is where I had said, right, that I said that if you have two lines, so that all same subset of points lie above it and below it, then it will intersect the same set of edges of the any spanning path. So, what you can do is for each of the such thing you just choose one line, and there will be n choose two such lines. So, those are lines, and initially I set the weight of each line to be 1, and then I double it. Okay. So, this is a construction. Now, I need to argue that this construction guarantees that no line in L intersects more than the square root of n edges. Yeah.
Where have you ensured that you are minimizing the QL?
I have not ensured that. I'm not minimizing, but I'm not saying anything minimize, but I will show you that this quantity is true. This part I am going to prove. Now, I have not done that yet. So, this is the algorithm. Now, I have to do analysis that the path I constructed, the crossing number is square root of n. And I will need 5 more minutes for this. Now, it is a double counting argument, right. So, let us look at the, let us say W I is a total weight of lines after ith iteration. Okay. So, what is the W 0? So, W 0 was initially the lines, it is a m, am I right, because there are m lines, m is n choose 2, but let us not worry about it. So, it is m. So, weight of each line is 1. So, total weight of the lines is m. Okay, so that is one thing. Now, other thing you notice is, other important relation is, what is, if I know W I, you need to write the, so you need to write the W I in terms of W I plus 1 in terms of W I. Okay. So, now one thing you notice is, when does the weight increase? The weight only increases here, right. This is the only place where I increase the weight. Now, and here is the fact I will use this as a cutting, because what you notice is the edge lies inside this triangle. So, if you look at the weight of these lines, since I doubled it, so if the weight of these lines, the lines that intersect this edge P Q also intersect the triangle, am I right? So, here is a triangle P Q, sorry, here is a edge P Q. So, any line that intersects this edge also intersects this triangle. Now, what I know is that since this is a cutting, the total weight of these lines is what? Is W I over R I, am I right? So, what I know is that this is at most R I, and so this is, and R I was this quantity. So, this is alpha, and N I was, let me write it was, where is N I, is this quantity N I plus minus I plus 1. So, what you get is okay. So, now if you expand it, what you get is W n after you finish the whole thing, or W n minus 1 because there are n minus 1 phases, will be W 0 and 0 to n minus. Okay, I might be messing the, yeah, okay, 1 plus alpha 1, and this you can rewrite as, just reverse in the reverse order because it will be little easier to write. So, I just writing the series in the reverse order, that is all I did. Now, this quantity you can write as right, 1 plus x is less 1 e to power x. So, then product becomes sum here, and so this becomes w 0 is m, I should m times. So, pi j is equal to 1 to n e to power alpha root j, this becomes e to power, this product becomes sum in the exponent, and sum is, you can think as an integral, and this basically becomes roughly alpha times the square root of n. Okay, so, because this becomes e to power sigma alpha over root j, j is equal to 1 to n, and if you integrate 1 over square root of j I up to n, you get a square root of n, right. So, that is what happens. So, this is becomes alpha times. Okay. So, this is one thing that you get. So, this is a final product. Now, on the other hand, suppose if a line intersects k edges, if a line intersects k edge, what will be its weight? 2 to the power k, am I right? So, if a line intersects k edges, its weight will, because every time it intersects an edge, you double its weight. So, if you double it k times, it will 2 to the power k. So, it means if you have a crossing number, if line intersects at least k times, the total weight of lines will be at least 2 to the power k. So, this is on the other hand 2 to the power k. So, what you know is that 2 to the power k is m times exponent n. Now, if you take the log on both sides, you are going to get I will k to be the square root of n.